right, so let's go ahead and finish this up, second part of this. So in the first section here on page 184, it says the power rule for arbitrary real powers. So we are still looking at the derivative of x to the n, okay? And we have obviously learned this. And we had extended this from positive integers to negative integers. So the last time we visited this, we had said it was good for all rational n number, and n is a rational number. Okay, so now we're going to extend this all the way out to arbitrary any number, any rational or any irrational number. So we're going to say that this works now for any real number, really. Okay. So let's go ahead and quickly go over a couple of examples here. Example number 5. Example number 5, it says A, find if x to the square root of 2. Let's go ahead and take the derivative of this. So the derivative of this is going to be nothing more than this, x square root of 2 minus 1. Okay, so that would be A. And then in B, we have 2 plus 3 sine x, sine 3, oh, 2 plus sine 3x, I'm sorry, 2 plus sine 3x to the pi power. We're going to go ahead and take the derivative of this. So it's going to be pi 2 times sine 3x to the pi minus 1. Then I have to take the derivative of what's inside here, which is going to be cosine 3x. Then I have to take the derivative of what's in the 3x. So I have to take the 3 out also. So I take so the 3 is going to show up over here. Okay? So I get 3 pi 2 plus sine 3x to the pi minus 1 times cosine 3x. So we had to do the chain rule 3 separate times, right? Okay? So once in here, and then we did the sine x, and then we have to do the 3x again. So we had to do the chain rule 3 times, okay? Okay, so what's of particular, I'm not going to do example number 6, that one so it's pretty simple. So I'm going to have you guys just review that, okay? Let's go to example number 7. Let's jump to example number 7, okay? Example number 7, it says, let's go ahead and see if we can take the derivative of x to the x. So obviously this is, we're in a conundrum here, right? Because we have x here, but we also have x in the, up in the exponents also, right? So in order to get rid of this, what we're going to do is we're going to go ahead, we're going to call this y. So y is equal to x to the x. And what we're going to do is we're going to go ahead and take the natural log. And what this accomplishes for us is it gets rid of the exponent, the x in the exponent, right? So I take the natural log of both sides, I'm going to get this is equal to natural log of x to the x, where now, like I said, this x can come forward. And this is the power, this is the beauty of taking the natural log, right? Because now I do not have that x here that was the problem for us. Okay, so now I can go and take the derivative. But now when I take the derivative, I no longer have an explicit derivative. I'm going to have an implicit derivative because now I am not given y straight off what it is. So now I'm going to take the derivative of this guy, which is going to be 1 over y. But then I have to apply the chain rule and say y prime is going to be equal to the derivative of this guy. And this is just nothing more than the product rule, right? So I'm going to take the derivative of this, which is 1, and then bring this guy down, plus this guy, and then take the derivative of this guy, right? 1 over x, and so this is going to be 1 over x. This is what I'm going to end up with. So this is going to end up be what? Natural log of x plus 1, because these two cancel out. So I'm going to get this guy here. So I'm trying to solve for y prime. So y prime is going to be y times natural log of x plus 1, where y was this guy. So now I can go ahead and substitute that back in and get x to the x, natural log of x plus 1. Okay, so this is kind of fun, all right? Now this guy here, you know, again, when you see something like this, you should immediately think, since I have x in the base and the exponent together, I'm gonna go ahead and take the natural log, okay? And this is one of my favorite questions on a test. So something like this is going to be on a test, okay? And I think in your homework assignment, there are quite a few of these, and they are, where are they at? Yeah, so they're in 47, 48, and 44, 43. So somewhere around that area, okay? So when you see those, pay close attention, make sure you understand how this works, okay? All right, let's move on to example number 8, the last one. Example number 8. Example number 8 says, the spread of a flue in a certain school is modeled by the equation that P of t is equal to 101 plus e to the 3 minus t. And as you look at the graph of what that looks like on the left-hand side on figure 4.18, you can see that this is clearly a logistic function. It's a logistic function, all right? So then this is what the function is, where P is the real total number of students infected T days after the flu, okay? So what was this 100 called? Anybody remember what this was called, the 100? There's a specific word for this. When we did the logistic functions, anybody remember the word called carrying capacity? This is the carrying capacity. Okay, at most, there can be 100 people there, right? Okay, so A, estimate the initial number of students infected with the flu. So A, the initial number would be nothing more than P to the 0, right? When T is equal to 0, right? So T is equal to 0, I get 100, 1 plus e to the 3. If I do this, what do I get? It's about 5. So you get 5 students. Pretty simple. B, how fast is the flu spreading after 3 days? So what are we looking for? We're actually looking for how fast it is spreading. So we're looking at P prime, but when T is equal to 3, right? That's what we're looking for, right? So let's go ahead and solve for P prime T, and then we go ahead and put T is equal to 3 in there, right? So P prime is this prime, so 100 stays there. Then I have to take the derivative. So this is, I'm gonna go ahead and rewrite this a little easier. So it's gonna be 100, 1 plus e to the 3 negative t to the minus 1. And I'm gonna take the derivative of this guy. So the minus comes forward. The minus is right there. And then I took care of the minus there. We get 1 plus e to the 3 minus t to the minus t. That's the power rule. Okay, now I have to take the derivative of the inside here, right? So I have to take the derivative of e to the 3 minus t, and this is going to be e to the 3 minus t. Then I have to take the derivative of the inside here, and it's going to be, if I take the derivative of 3 minus t, I get -1, and that -1 is going to cancel out with that guy. Okay, so this is what I'm going to get. So let's go ahead and put this in when P prime, when t is equal to 3. I'm going to get 100, 1 plus e to the 0, negative 2, e to the, when t is equal to 3, this is 0 again. E to the zeros are nothing more than 1s. So I can go and get rid of this. And this guy is going to be 1. So I'm going to get 100, 2 to the negative 2, which is going to be 4 down on the bottom. So your answer is 25. 100 divided by 4 is 25. C, when will the fluid spread at the maximum rate? And what is this rate? So if you go ahead and graph this using what? What are you going to use? You're going to use the ender, right? If you do the ender and you take the derivative and graph that, you flip the page and you get page 180, on page 186, you're going to get that graph. If you look at that, it just so happens that the maximum, it happens when t is equal to 3, and we've already calculated that to be 25. Okay? And in chapter 5, we'll find out how to do this numerically. Okay, we'll find out how to do that numerically. But for now, just know that you can graph it and you can just find out, try and find out where it is the maximum. All right. And that is the end of part 2. Were there any questions there? All right, we're good then. Where am I?